external magnetic field. Let us consider a uniform magnetic field of strength B. Let a charged particle of charge Q be projected into the magnetic field with a velocity v perpendicular to the direction of the magnetic field. When the charged particle is moving perpendicular to the magnetic field, the charged particle experiences maximum force, and this force is acting perpendicular to both the magnetic field and the velocity of the charged particle. The magnitude of the force acting on the particle F is equal to BQV sine theta, where theta is the angle between the direction of the velocity and the direction of the magnetic field. Since, in this case, theta is equal to 90 degrees, sine 90 is equal to 1, the force is denoted by F is equal to BQV. We know that when an external force acting on a body is perpendicular to the motion of the body, the work done on the body is said to be zero. In other words, in the expression for work done, W is equal to Fx cos theta. If theta is equal to 90 degrees, we get W is equal to 0. In the case of a charged particle in a magnetic field, the magnetic force is acting perpendicular to the direction of the velocity, and thus the work done on the charged particle is zero. As the work done on the charged particle is zero, there is no change in the kinetic energy of the charged particle, and the magnitude of the velocity of the charged particle remains constant. As the magnetic force acting on the charged particle is perpendicular to both the direction of its velocity and magnetic field, the charged particle moves in a circular path, and the magnetic force acts as a centripetal force. Thus, the centripetal force F is equal to BQV. By definition, the centripetal force is denoted by mv square by r, where m is the mass of the charged particle, v is its velocity, and r is the radius of its circular path. Equating these expressions, we get the radius of the circular path r is equal to mv by bq. Let us label this as equation 1. When the momentum mv of the particle increases, the radius of its circular path also increases accordingly, as b and q are constant. Hence, the radius of the circular path of the charged particle moving in an external uniform magnetic field is directly proportional to the momentum of the charged particle. The charged particle executes uniform motion with a fixed time period t and angular frequency omega. Here, omega is equal to v by r. Let us label this as equation 2. Comparing equations 1 and 2, the angular frequency of the charged particle omega is equal to bq by m. Let us label this as equation 3. As you know, the time taken to complete one revolution is called the time period of revolution. Time period t is given by 2 pi by omega. Substituting equation 3, we get t is equal to 2 pi m by bq. From the expression, it is clear that the time period of revolution of the charged particle is independent of its speed. The reciprocal of the time period is called frequency, that is, f is equal to 1 by t. Substituting t in the expression, we get F is equal to BQ by 2 pi m. This frequency is called cyclotron frequency. Now, consider that the charged particle is projected at an angle theta with a uniform magnetic field, which is anything other than 90 degrees. In this case, we need to resolve the velocity into two components. One component parallel to the magnetic field dV and the other component perpendicular or normal to the magnetic field dN. Since dV is parallel to the direction of the magnetic field, we have Vp is equal to V cos theta. As Bn is perpendicular to the direction of the magnetic field, we have Vn is equal to V sin theta. The component of velocity Vp along the magnetic field remains the same because the angle between the parallel component of the velocity and the direction of the magnetic field is zero, and hence there is no force acting along the magnetic field. The charged particle moves along the magnetic field due to the parallel component of velocity Vp. At the same time, due to the normal component of velocity Vn, the charged particle moves in the circular path with radius r equal to m into Vn by bq. Thus, the charged particle has a velocity in the direction of the magnetic field and also in a circular path whose plane is perpendicular to the direction of the field. Due to this, the resultant path of the charged particle is a helix. The radius of the circular path during the helical motion is called radius of the helix. Here, the axis of the helix is along the magnetic field. The distance moved by the particle along the magnetic field during one rotation in the helix is called pitch. Pitch P is equal to the product of a parallel component of velocity and the time taken to complete one revolution, which is a time period of revolution. Substituting T is equal to 2 pi m by bq in the expression, we get P is equal to Ve into 2 pi m by bq, which is equal to 2 pi